Again, welcome to lecture number 2. Again, welcome to lecture number 2. In this lecture, we are going to learn about continuous functions and also limits at infinity when we are using infinity. Previously, we went through limit approaching any value. It can be a positive, negative value, 300, any value. We also have a limit when it approaches infinity, either positive infinity or negative infinity. And we shall go through that also. So again, this is continuous functions. How do we determine if a function is continuous or discontinuous? And also limit at infinity. So we start with the continuous function first. Here we said that from the previous lecture, which is lecture 1, we have found that f at c is the same as limit as s approaches c for any polynomial function f at c and a real number c. So any function for which this special property holds, again, is called a continuous function. So we can say a c have to be a real value, a finite value, 6, 7,000, any value. So that would be a continuous function. Now, if the function is a polynomial function, now sometimes we may have a discontinuous function when we have a rational expression, let's say a value divided by another value, let's say function f at x divided by g at x. If g at x is 0, we may have a discontinuous. Also, if we have a radical, we know the radical values have to be a real value. It cannot be a negative value. Square root of 0 is 0. But square root of a negative value or cube root of a etc. So again, we will go through this, we will do example. So let's go through the first theory here, continuity at a point. Now, we said that a function f is continuous at x equal to 6 if the following 3 conditions are met. First, we have to make sure that f at c exists. We know what we mean by f at c exists. For example, if I have a limit x approaches c, f at x, if there's a solution, that means it exists. Sometimes there will be no solution, it means it's not existing. Second is, if we have a limit as s approaches c, f at x exists, as I said earlier. Then also, if we have a limit f at s as s approaches c equal to f at c. So we can see that on these 3 conditions means that if we have a limit of any function, if that function exists, if there's a solution, that means we have a continuous. If there's no solution, it's discontinuous. So if one or more of the conditions above do not hold, we say the function is discontinuous at x equal to c, at s equal to c. So the diagram you can see here, again, we have a continuous function. You can see there's no any broken line, so y equal to f at x. At c, we have f at c, so this is a continuous. Now, if a function is discontinuous at one or more points, it is called a discontinuous function. So we can see some of the examples here. Let's see the first one. If I have f at x equal to 1 over s minus 2, if s equal to 2, the function or even the limit does not exist, because here we are going to get a value divided by 0. So if f at 2 do not exist, then it's discontinuous at when s is 2. We have another one here, also the same concept, but here we have more or less a parabola. But we can also see here that the denominator is s minus 2. So if s equal to 2, it doesn't exist. And here also we have a piecewise. So we have 4 minus x and 4. But here we are saying whether s is not equal to 2 and is s equal to 2. We can see that if we substitute 2 here, we get answer 2. But here is 4. So it does not exist. Since 2 is not equal to 4, the piecewise function does not exist. We learn about this condition in lecture number 1. So these are some of the examples where a function is discontinuous. A function is only discontinuous if that function's solution does not exist, as we can see these 3 examples. So here, if f is a polynomial function, then limit s approaches c f at s equal to f at c for every real number c. As we said again, if f is a polynomial function, then the limit f at s as s approaches c we substitute with x, so it's equal to f at c for every real number c. Now, limit h at x as s approaches c also equal to h at c. And if h at x equal to f at s by g at x, we call this a rational function. And this will only exist when what? The denominator, which is g at x, is not equal to 0. We studied this rule also in lecture number 1. So by definition, we say every polynomial function is continuous for all real numbers. And every rational function is continuous at all values if x does not make the denominator 0. Or here we say if all values of x except those that make the denominator 0. A rational function means a division, like f at x divided by g at x. If we can find g at s solution at any value except 0, then it's continuous. If it's 0, discontinuous. So let's see an example here. We have g at x. This is a piecewise function. Both questions are piecewise function. S plus 2q plus 1 when s is less than or equal to -1. And also g at x, 3 when x is greater than -1. So what we can say is that, again, we studied this law in lecture number 1. When you have a piecewise function, your solution have to be the same, then the limit exists. If the solutions are different, the limit does not exist. So I'm just going to do this very quick. I'll plug -1 at x here. So -1 plus 2 will give me -1. -1 cubed will give me -1. So -1 plus 1 will be 0. But the second is 3. So g at x does not exist. We have a discontinue at when s is -1. Now let's try the second one. 4 minus s squared less than 2, or s minus 2, s is greater than or equal to 2. So again, let's substitute the 2's here. So 2 squared will give me 4. 4 minus 4 is 0. The second one, we have 2 minus 2 is 0. Okay, so here we have 0, 0. So which means the b, f at s equal to 4 minus s squared if s is less than 2, or s minus 2 if s is greater than or equal to 2. It exists. Why it exists? Because the solution are the same, 0, 0. Here it does not exist. Why? Because the solution is 0 and 3. The rule said in piecewise functions, the solution have to be the same in order for the limit to exist. So that's the solution here. Again, it's explained here. G at s is a piecewise defined function in which each part is a polynomial. Thus, to see whether a discontinuity exists, we need only to check the value of x for which the definition of the function changes. That is, s equal to -1. So we plug -1 plus 2 to the power 3 plus 1, it gives us 2. Because g at s is defined differently for s less than -1 and s greater than -1, we use left and right hand limits. We will say that again, this function does not exist. So the answer is 2, but we have 3 for g at s, the second part, greater. So again, left and right hand limit does not limit g at s, again, does not exist. What we mean is the difference between left and right, let's look at the question, what we mean. You see, if x is less than, I think we did this in lecture 1. If s is less than or equal to -1, we leave from left, so it's negative. When it's greater than -1, actually the opposite, sorry, we mean this is negative. When c, so negative and positive of c, and that's what we mean here. But the goal here again, just plug in -1 to the expression here. Here we don't have, it's only 3, we don't have any variable x, so we can't plug anything. So our goal is that if the s plus 2 to the power q plus 1 is equal to 3, then the limit exists. In our case, it's not equal to 3, so limit does not exist, it's 2. Now let's look the second one, which we already went. The second one, we saw that the limit exists because we have 2 squared is 4, 4 minus 4 is 0. Then we have s minus 2, another 2, 2 minus 2 is 0. So both of them are 0. Because the left and the right limits are equal, we conclude that the limit s approaches to f at s equal to 0, and it exists. So next we move to the limit at infinity. So this is the rule here. If c is any constant, then limit s approaching positive infinity c equal to c. We are assuming c is a constant value. And also limit s approaches negative infinity c is also equal to c, because c is a constant value. Now, if I have limit s approaches positive infinity c over s to the power p will be equal to 0, only p should be when p is greater than 0. What we mean that p is greater than 0 means the exponent here should be 1, 2, 3, etc. And we can solve the problem. The same time approaching negative infinity, c over s to the power n, we have to make sure the power n is greater than 0 also. And we will see example. Okay, so this is 2 examples here. I see now there's a little bit slight difference between how to solve a limit when it approaches positive or negative infinity. You have 2s minus 1, s plus 2. So I'll look for the variable highest exponent value. In this case, it's 1. So which means I'm going to divide 2s by x, 1 by x, s by x, plus 2 by x. So here, saying the highest power of s to represent is s to the power 1. So we divide each term in the numerator and denominator by x, and then use the properties of limit at infinity. Since the highest is x, we divide everything by x. And this is what we get: 2s over x, 1 over x, s over s plus 2 over s also. Then we simplify it, we get s will cancel s2, s will cancel s1, 1 over s. Now, since s approaches infinity, what happens to 1 over x? It will be 0. The higher the value of the denominator, the lower the value becomes, so it's 0. So anytime we see something like this again, or even if it's 1 over x squared s cubed, still 0. So our final answer, we get 2 over 1, 0, 0. So we get 2. This is the properties 1 and 2. Now let's try the second one. Second one, we have s squared plus 3 divided by 1 minus x. But again, s approaches negative infinity. So we have to divide, look for the, now we have s and s squared. So we look for the highest exponent, which is s squared. Now, if I have s cubed, I'll use s cubed. I'll divide all the term by s cubed. The previous example, we have x, and x is the highest. So we divide everything by x. I mean, when I said everything, I mean both the numerator and the denominator terms. We divide everything by x. So here we get s squared by s squared plus 3 over s squared divided by 1 minus s squared minus s over s squared. Then we simplify it. S squared will cancel 1. We have 1 over s squared. SS will go here, so we get 1 over x here. Then we get, this will be approaching 0. So we take this out, but we have a problem now. You can see that here we couldn't get a single unit, like 2, 3 or something. So in this case, actually that's what we say. This limit does not exist because the numerator approaches 1, but the denominator approaches 0. Because again, as we said earlier, since this is approaching negative infinity, this will be 0, this will be 0, this will be 0, as we saw it in the previous example. I'm going back to the first example. See, 2x and x, so they cancel 1, 2x and s, 2. But here, 0 and 0. Here is 1. So the answer will be 2 over 1, which is 2. But here we get the denominator, both terms are 0, 0 now. And here is 1, 0. So we get 1 over 0. And we said earlier, any value divided by 0 means undefined solution. And also what? It doesn't exist. The limit does not exist. So also we have a concept of limit at infinity and horizontal asymptotes. Here we say that a limit s approaching infinity f at s equal to b, or limit s approaching negative infinity f at s equal to b, where what? The b is the constant. Then the line y equal to b is the horizontal asymptote for the graph of y equal to f at x. Otherwise, y equal to f at s has no horizontal asymptotes. So we have continuous functions and also limits at infinity. The following information is useful in discussing continuity of a function. One, we say the polynomial function is continuous everywhere. Remember, 2x squared plus 5 minus, since we are not dividing by any value to say, okay, dividing by 0, no existence or radical. So a polynomial function is always continuous everywhere. But a rational function is a function of the form f at s over g at x. And when g at s equal to 0, then it's discontinuous because the limit does not exist. So we have to make sure if g at s is not equal to 0 at any value of x, then the function is continuous everywhere. But when it's equal to 0, the function is discontinuous at x equal to c. Or if g at c equal to 0 and f at c not equal to 0, then there's a vertical asymptote at x equal to c. And also if g at c equal to 0 and the limit f at s over g at x as s approaches c equal to l, then the graph has a missing point at c and l. So a piecewise function normally may have a discontinuity at any x value where the function changes its formula. So the following steps are useful when we are evaluating limit at infinity for rational function p at x divided by q at s. So we divide both p at x and q at s by the highest power of x found in the polynomial. And that's what we did earlier. Then use the property of limit at infinity to complete the evaluation. So this will be the conclusion of limits at infinity, and also when a function is continuous or discontinuous. As we said earlier, a function is continuous when the limit exists. Let's say limit s approaches c f at x exists. Or when you have a function f at c exists or f at x exists, then limit is continuous. Limit is only discontinuous, or the function is only discontinuous. Normally we say the limit does not exist. It means the function is discontinuous. Only, again, only. For example, we have a rational function, which means we are dividing by some value, the denominator. Now, if the denominator is 0, we have discontinuity. Or if we have a radical expression and the value is negative, less than 0, then we have discontinuity. So again, wish everybody the best, and we will soon go to lecture number 3. So thank you. Again, one thing I forget to mention is that we are starting our textbook at chapter 9. So this is chapter 9-2, which is my lecture number 2. We're going to move to the next chapter, 9-3. So again, thank you. Bye.